Hello everyone, I'm Professor Harrison and welcome back to our module on regression. Today we're going to extend the model from a single explanatory variable to several of them at once. This is called multiple regression, and it's really where regression starts to earn its keep. We're following Margot, a graduate student trying to reassemble a story that her family buried. Today she's working a housing dataset, trying to pull apart the separate effects of two things that tend to move together. She turns to the next problem in her coursework. So far, every regression we've run has had one explanatory variable. So we get one input and one output, and it only has one slope. Multiple regression is just the natural extension of that. Instead of explaining the outcome with a single variable, we explain it with several of them at a time. The model looks exactly like you'd expect. The outcome equals an intercept, plus a coefficient times the first explanatory variable, plus a coefficient times the second explanatory variable, and so on for as many variables as you want to include, plus the error term. Each explanatory variable gets its own slope coefficient. Now, the reason you'd want more than one variable comes down to a problem with the real world. In the real world, things tend to move together, and if you leave one of them out, the variable that you kept ends up quietly absorbing the effect of the one that you dropped. So let's make this concrete. Say we're trying to explain house prices, and we have two things that we can work with. The first is the square footage of the house, and the second is the number of bedrooms. Here's the thing, bigger houses tend to have more bedrooms. So the two move together. So if you want to know what one more bedroom is actually worth, then you have a problem, because bedrooms and size are very tangled up. So it's difficult to parse out how much is attributable to the bedroom versus the square footage that a bedroom adds. With simple regression, we wouldn't be able to tell these two effects apart. But with multiple regression, we can actually parse these things out. Let's try running it in both ways to see what happens. First, let's regress on the number of bedrooms by itself. Say that it gives us a fitted line of $80,000 plus $50,000 for each bedroom. So this simple model says a bedroom is worth $50,000. But think about what $50,000 is actually capturing. When you go from a 2-bedroom to a 3-bedroom house, you're almost never just adding a bedroom. You're also adding more square footage. So that $50,000 isn't just the value of a bedroom. It's the value of a bedroom plus the extra size that comes naturally with it. Now let's add square footage to the model and hold it fixed. Say the multiple regression comes out to $30,000 plus $120 for each square foot plus $15,000 for each bedroom. Look at what happened to the bedroom coefficient. It dropped from 50,000 down to 15,000. And that drop is the whole point. In multiple regression, the 15,000 is the value of one more bedroom for two houses that are the same size. We've held the square footage constant, so the bedroom coefficient can't borrow any credit from the size anymore. The $35,000 difference between the two models was square footage hiding inside the bedroom number the whole time. This is the key idea for interpreting any coefficient in multiple regression. Each coefficient is the effect of its own variable holding all the other variables fixed. People call this the partial effect or the ceteris paribus interpretation, which is just Latin for all else equal. The $120 is what one more square foot adds, holding all the bedrooms fixed. The $15,000 is what one more bedroom adds, holding all the square footage fixed. So this changes what you actually do with the numbers. If an appraiser is pricing a 500 square foot addition that doesn't add a bedroom, then the number to use is the $120 a foot from the multiple regression, not the inflated figure that you pull up from a model that ignores the size. Having multiple regression hold all the other variables fixed is what makes the coefficient mean what you want it to mean. One last thing is worth flagging. We just watched the bedroom coefficient change depending on whether square footage was in the model. That's not a quirk of this dataset. Leaving out a variable that belongs in the model is a real in-name problem, and we're going to come back to it more formally later in the module. Margot closes the problem set. She's been staring at her grandfather's returns for weeks, and the thing that always stopped her was that everything moved at once. Now she has a tool that she can use to hold all the rest of it still and look at each piece on its own. So that's multiple regression. You can put several explanatory variables into the model at the same time, and each coefficient then measures the effect of its own variable while holding the other ones fixed. That holding the rest fixed part is exactly what single variable regression can't do for you. When you leave a relevant variable out, the ones that you kept end up absorbing the effects of the ones you omitted, and your coefficients stop meaning what you think they mean. Multiple regression is what lets you separate these effects that are all tangled together in the real world.